Well, hello and welcome. In this video, I'll be covering sections 9.1 and 9.2, which are over solving systems of equations. My goal for you by the end of the video is to be able to have a solid understanding of both the substitution and elimination strategies for solving either 2-variable or 3-variable systems of equations. So we'll start with talking about what systems of equations in 2 variables happen to be and what will be some of the terminology that we have that pops up. So just a reminder, a system of equations is essentially when we have multiple equations, 2 or more, that we're trying to figure out what their possible intersecting points are simultaneously. So basically what we'll be looking for is any and all ordered pairs that make every single equation that I have a true statement. Some of the terms that we have that go along with it will be if I have at least one solution, we call it consistent. If I don't have any solution, we would say it's inconsistent. And in addition to that, if I know I have exactly one solution, we would be able to add on the word it's independent, or if it had many solutions, it would be dependent. Generally, the many solutions situation is when I actually have 2 of the exact same line, even though they maybe appear to be 2 different lines just because of their formatting. So again, this is just some terms to be aware of and hopefully understand, but isn't going to necessarily make or break what's going on. It's just a matter of if you happen to see these phrases, at least connecting what that would mean to you. Now, I probably should have mentioned this on the previous slide, but feel free to pause anytime if there's multiple things. If I go through it too fast, go ahead and pause and write things down as need be. This is an example of one of those times. I'm just going to kind of paraphrase what each of these strategies are. Substitution approach, generally speaking, is where I'm going to start with, let's say I had 2 equations. I would pick out of those equations one of them to isolate a variable with, whether it's an x or a y or any other variables that maybe are provided, does not matter. So essentially you just kind of look for, out of the equations that have been provided, which one looks like it would be the easiest to isolate something with. Once I've done that isolation, I then would replace that variable in the other equation that I haven't dealt with, or even equations, and substitute it in, so then I only have the one variable left that I should then be able to solve if it truly has a solution. Elimination, on the other hand, is more where I'm going to need to line things up appropriately, so kind of make each equation be in the exact same formatting from left to right. That way my x's are lined up above x's, my y's are lined up above y's, the equal signs above equal signs, and constants above constants, for example. And then from there it would just be, let's look to see if there's any way I can make the coefficients match, and we then scale up or scale down whatever the functions are by multiplication or division until I can get the coefficients to either be perfect opposites or exactly the same, and then make the decision of whether I should add or subtract to eliminate. And hopefully as I work through the example of that will make a little bit more sense when you actually see it in action. But as far as the step-by-step process, like I said, feel free to pause it here, write these down if you need to have that reference. But as a general idea, we're just going to try and make it to where somehow, some way, I only have one letter left so I can solve that equation. And once I have that first solution, we'll back substitute until I can get what it's paired with, or in this case, an x and a y, which we again call either a point or an ordered pair. All right, let's go ahead and move on to our first example here, which wants us to model utilizing substitution. So substitution as a general approach is going to be, how do I get a variable by itself in one of the equations I see? Here it looks like it's equally level of difficulty to get x or y by itself. I think I'm going to go after the x though by adding y over. That way everything stays positive. So that gives me our x equation, which would be it's equal to y plus 5 after I add the y over. And then now that opens up the ability to, everywhere I see an x, put what it's equivalent to, which we just said was y plus 5, and then rewrite. So this would now be 2 times our parenthesis y plus 5 plus our y equaling 1. So now from here I'm going to go ahead and distribute things through. So it looks like I can take the 2 through. It gives me 2y plus 10 plus y equaling 1. And then now from there it looks like I should be able to combine some like terms. So in the next line I'll just go ahead and say 2y and y, that turns into 3y. And then I could probably subtract the 10 the other direction and turn that into 1 take away 10 is negative 9. So now we're down to at least just one more step to go. In this scenario, it looks like all I have to do is just divide both sides by 3. and I get that my y value is -3. So unfortunately we're not quite done yet. We've got half of our answer. Keep in mind our ordered pair needs to have both an x and a y. We've at least got half of the answer. We just need to now go back and back substitute to get the other part. And that's actually where our first decision, where we isolated x, will come back and become a little bit more helpful. In this scenario, I can go ahead and say up here I've got x is equivalent to the y, which I just found to be -3, plus 5, and that would give me a value of +2. So now what we'll do for our final answer is just put it all together, and my ordered pair would be the x, which was 2, paired with the y, which was -3, and there we go. That would be our solution set. Now we can always double check our answers by back substituting into the original as well. We can check it with the top one. To take away a -3 does in fact give me 5, so that part checks out. And then the second one, 2 times 2 is 4, plus a -3 does in fact equal 1, so yes, that solution is good. All right, let's try another example, but this time modeling using the elimination approach. So if I wanted to eliminate a variable, that's more where I'm going to try and make coefficients either become opposites or become the exact same. So this usually involves just scaling up or scaling down by multiplication or division. Why substitution for this problem, just to kind of talk on that point, why this would actually be a little bit tougher to do a substitution approach with is because if I were to isolate either x or y in either of these equations, I definitely will get some fractions as coefficients on either the x or the y, whatever is on the other side. And just anytime fractions get involved, we have more things to worry about, such as common denominators or just how I would divide or add or subtract or multiply. So it just is going to be a little bit more difficult if I did do this substitution approach. It would still work, it's just maybe not as simple. So elimination as our strategy, what we'll try and do is just pick one of the letters to kind of go after. It looks like it's about the same level of difficulty to get the x's or the y's to eliminate. And by that I mean I just need to get the coefficients to either match or be opposites. So if I went after the x's, I could make them both have a 20 in front by multiplying the top one by 5 and the bottom one by 4. Whereas the y's, I can make them match with a 6 by multiplying the top one by a 2 and the bottom one by a 3. So I think just because those numbers would be a little smaller, I think I'm going to choose that strategy and go ahead and multiply the top one by 2 and then multiply the bottom one by 3. This isn't necessarily the best mathematical notation, but the idea of what we're trying to accomplish still is hopefully getting, or at least is coming across. So now all I'm going to do is just distribute it through and actually rewrite the equations, keeping in mind I want to make sure that the formatting that I have, where x's are above x's, y's are above y's, and my equal signs are lined up and my constants are lined up, I want to keep that so the vertical adding or subtracting that I'll do afterwards is a little easier to follow along with. So if I distribute the 2 through the top one, I get 8x plus 6y equaling 22. And if I distribute the 3 through on the bottom one, I get a -15x, a positive 6y, and that would equal a 45. So now what I'll want to do is find a way to either add or subtract to eliminate those y's that I just created. Here, if I go ahead and subtract, I'm going to go ahead and distribute a negative through, if you want to think of it that way as well. But I'm going to subtract these terms one at a time. So this would be 8 take away a -15, which actually would switch to addition. So that's going to take me up to 23x. 6y take away 6y does zero out the way I wanted. And then on the other side, I've got 22 take away 45. That would actually take me down to -23. So as we can see, the next step, I'm going to be able to isolate the x just by dividing by 23. And I get that my x coordinate apparently will equal -1 for this solution set. So now all I have to do is just figure out what the y is going to be, and at this point we have a decision to make as to where I want to plug back in. So for this one, it doesn't seem like there's really one that stands out to me over the other. I think I'm just going to pick the top one and go. So if I go ahead and pick the top one and substitute in, it would be, let's see, where can I do that off to the side here? It's just going to be 4 times the x I just found, -1, added with 3y equaling 11. And then now start just moving terms around and simplifying or trying to isolate the y. So if I've got a -4 like that, I would add 4 to cancel that part out. That way I get 3y is now equal to, if I add that up, I get 15. And then the last step would be divide the 3 over, and I get that my y coordinate will be 5. So now from here I can go ahead and bring this back together. Keep in mind, again, our answer here is an ordered pair, where it would be our x-coordinate first, -1, paired with our y-coordinate second, 5. And voila, we've got our ordered pair. And we can always, again, double check just by plugging it back in. But in interest of making this video not last as long, I'll let you guys go ahead and do that check. Now there are two special cases that I kind of mentioned on the very beginning of this video, such as having either no solution or having infinitely many solutions, that did not happen in either of the two examples I've worked through yet. But just as far as to talk about when that would happen, without actually working through an example, how we would be able to make that statement or determine which statement to make depends on if I were to go through and do either a substitution or elimination approach. And I notice when I get going with either trying to eliminate or substitute, all of the variables essentially just kind of cancel themselves out, or have like an opposite somewhere that when I combine it zeroes itself out. At that point I would go ahead and say, based on what I see, whether it's a true statement or a false statement, whether it's going to be an infinitely many or a no solution. So again, for example here, the first statement as it says here, if you got something true such as 0 = 0 or 10 = 10 or 5 = 5, anything that you know is for sure true, for example, any number always will equal itself, we can go ahead and say that must be an infinitely many solution set. If I get something that comes back false, such as 0 = 7 as this says, or any other statement where it's a number equals something that's not identical, then you can go ahead and commit to that must be a no solution situation. Alright, now let's move on to solving our other type of system, which is a system of 3 variables. So as we can see on this screen, this is now going to be something where I have the format where it's got 3 terms with different variables. So could be potentially x, y, and z, but doesn't have to be. But as far as the general format, it would be all 3 of those terms grouped together, ideally in alphabetical order on the left side with potential coefficients that are different, and then being set equal to some number on the other side where everything just needs to be real numbers as those coefficients or constants. The solution for any of these systems of 3 variable equations now is not what we would call an ordered triple. As you can see here, we just order them alphabetically, so x first, y second, z third, if that happened to be our 3 variables. And ultimately, I'm just looking for any points in that format that would actually make all 3 equations true, or even more. If there were more equations, I just need to find what would make all of them happen to be a true statement. So kind of similar to what we had with the 2 variable system, we do have in this 3 variable system as well the ability to have a single solution. We could have infinitely many solutions. There's actually now a couple of scenarios where that would happen. Or we might have a no solution. And again, the next slide I'll go ahead and give you some visuals of what those would actually look like. So like I mentioned in the previous one, it's just a matter of having a couple of visuals of what these actually would look like. Really, you can kind of pause and read through each of these if you really feel like it, but the general ones that we're going to probably see the most of are going to be like the one solution situation in the top left, where I have 3 different planes that all just cross over each other at a single point, so we're just trying to figure out what that single point is. Like I mentioned though, there are the no solution and infinitely many solutions, which are kind of modeled as you can see here. I won't go too much more into description of it, just as far as like what these things look like, that's all I'm kind of including that for. Alright, so let's go ahead and just maybe talk about some of the things that I'm allowed to do, or at least as far as some of the rules that I would need to follow. Some options I now have, since I will have 3 equations instead of 2, is I could rearrange them however I see fit. I can also move terms from one side of an equal sign to another, just like any other equation. And we also can scale up or scale down, just like we did with the elimination strategies before. And then the third one here basically is just saying if I pick 2 equations and add it with a multiple of another, I can create a new equation that potentially would have fewer variables. So kind of the idea here is if I'm starting with 3 variables, we want to find a way to try and get rid of one of them so I can turn it into a 2 variable system. And whether you want to do that with an elimination approach by like trying to cancel out, say, maybe the x's between 2 equations, or maybe you wanted to try and do more of a substitution approach, which would be more like maybe you want to isolate an x in one equation and then plug that into the other 2 equations, is kind of up to you as far as how you want to go. More than likely, if this is brand new to you, this probably makes zero sense so far, but I'll try and model both in the next example so we can kind of see like here's the approach that we can have. But there is no like really one set way of having to do this. It's more just a general approach and what we're trying to accomplish. Initially, we're trying to make 3 variables turn into 2 variables. And then once I have that 2 variable system, I try and turn it into just a single variable. And once I have it there, I should be able to solve for that. And then it's a bunch of back substitution back through any of the equations I created or were able to find to come up with whatever the next unknown would be. And in the end, I'm just trying to figure out what the trio or the ordered triple would be, and then put it back together as an ordered triple where x is first, y is second, and z is third. Okay, let's go ahead and jump into an example of how these systems of 3 variables work. So I'll go ahead and model this both ways. I'll model this using a substitution approach as well as using an elimination approach. This first example, I'll go ahead and let's just label it here. This is the substitution strategy I think I'll start with here first. Where again, as far as what do I want to accomplish or what am I going to try and accomplish, I essentially want to pick one of the equations, isolate a variable, so I can then replace that variable in the other equation. So it looks to me like either the top one or the bottom one are relatively easy to isolate a letter with. I think I'm just going to commit to the top one, get x by itself by moving these 2 terms over, one by adding, the other by subtracting. And I get that my new expression is going to be x is equivalent to a positive 2y, a negative 3z, and the positive 11 that's already on that side. So now what I'm going to do is basically just take that expression that I know x is equivalent to, identify the other x's I have in the other equations, which are those 2 that I just underlined, and actually substitute in and simplify. So if I go ahead and do the first one, it would be 4 times what we just found, 2y minus 3z plus 11. Then I have all the other terms, plus 2y minus 3z equaling 4. And then try and simplify. So if I distribute that 4 through, looks like I'd end up with 8y take away 12z plus 44, and then still having the other 2 terms on this side, positive 2y minus 3z equaling 4, and then start moving some terms around and combining like terms. So it looks like I've got a total of 8y and 2y for 10y, negative 12z minus 3 more z is negative 15z, and I can probably move that 44 over to the other side by subtracting 44. That way it's no longer there, and I would have 4 take away 44 is negative 40. Go ahead and change color just to differentiate. I'm going to do the same thing with the next equation, or the bottom equation, which would be, let's plug in the same thing, 2y take away 3z plus 11 in place of the x. Then I've got plus the 3y minus the z equaling still the 4. So just like before, I can distribute that 3 through. I'd end up with 6y take away 9z plus 33 plus 3z minus, or sorry, 3y minus z equaling 4. And then it looks like I probably will be able to move the 33 over and then combine some y's and z's. So 6y and 3y, that would take me up to 9y. Negative 9z minus 1 more is negative 10z. And then 33, if I take it away from 4, would take me down to negative 29. So now what I'm going to do is just take the 2 equations I created. Notice I have now 2 equations with only 2 unknowns, so I have at least accomplished getting the x out of the way momentarily. I'm going to go ahead and just line them up and just see what strategy makes more sense. I think I might switch to an elimination idea at this juncture, just because it looks like I might be relatively easily be able to get the z's to match. So getting those things lined up, I'm going to go ahead and now look to see what can I do. If I look at the y's, I got a 10 and a 9. I can make them both 90. That seems a little large. The z's, I've got a 15 and a 10. I think I can make them both 30. So that seems like the smaller option. I'm going to go after that one. So all I would do is multiply the top one then by a 2, multiply the bottom one by a 3, and rewrite those 2 things somewhere wherever I might still have room. So I've been writing a little bit too large. I got to find a way to maximize my space here. So I'm going to go ahead and use the left side here. Multiplying the 2 through, I get 20y minus 30z equaling negative 80. And then the other one, I get a 27y minus a 30z equaling, and 3 times negative 29 would be negative 87. So if I now look at what we've got, we just need to find a way to eliminate some stuff. So here it looks like I could probably just subtract vertically. I could do the bottom one minus the top one, or the top one minus the bottom one. We can rearrange that whatever way I want, but I think I'll just keep it as is. 20 take away 27 is going to go negative 7y. Negative 30 minus a negative 30 does zero out the z's. And then negative 80 plus 87, because of the double negative, would actually make that positive 7. So it looks like all I have to do is just one extra step here of dividing by negative 7. And I get that my y coordinate's going to be apparently negative 1. So then now what I want to do is start cycling my way back through equations so I can isolate other variables. So I'm going to stick with the 2 variable options, the 10y minus 15z equaling negative 40, or the 9y minus 10z equaling negative 29 there in the middle of the screen. That should allow me, if I substitute in place of the y, to solve for the z. So let's go ahead and do that really quick. If I do that substitution, let's see, I've got 9, I'll go with the top one, I guess. 10 times negative 1 minus 15z equaling negative 40. Since that's a negative 10, I would just add 10 to cancel that term out. And then I've got negative 15z equals negative 30, and divide the negative 15 to get a z value now of 2. So I've got 2 out of the 3. Now what I can do is go back up to the x equals statement I had at the very beginning, which if I go ahead and do that, that's now going to be x is equivalent to 2 times the y I found, which was negative 1, minus 3 times the z I found, which was 2, and then plus the 11. So if I go ahead and simplify that, it looks like I get negative 2 minus 6 plus 11. So that's a negative 8 plus 11, which is 3. So then my ordered triple, if I go all the way back up to maybe right underneath the instructions there, I'll go ahead and write it up in this area, top left. My solution set now is, I found the x was 3, I found my y to be negative 1, and I found my z to be 2. And at that point, that would be my system solution, and we can always double check by plugging it into all 3 and just seeing if I get a true statement. But for this one, I promise we do. Alright, as I mentioned earlier, I'm going to go ahead and just solve this a slightly different way. This time I'm actually going to do more an elimination approach, where elimination is generally where I'm trying to actually combine things by adding or subtracting. So picking 2 equations, adding or subtracting to eliminate a variable. I just will have to do it a couple of times so I can potentially turn into a system of 2 variables where I now have 2 equations. So I personally like to kind of number our equations, or the equations I'm dealing with, so I can keep track of which pairs I've already used. So we could do any possible pairs. I just needed to pick 2 and then find a way to eliminate the same variable. So I think I'm going to start with, let's get equation 1 and equation 2. And I'm going to go ahead and I think I'm going to go after the z's with this one, but the y's look like they're just as easy. So I'm going to go ahead and just remind myself I'm eliminating the z's with those. They already are opposite numbers, so I should be able to just like stack it up and add. And that will accomplish the goal initially here of eliminating at least my z's. I think I actually kind of get lucky with this one, in the fact that it actually will also eliminate the y's, which is not always going to happen, but it does happen to happen here. So here, notice if I wanted to eliminate the z's, it would be addition that would happen. X plus 4x, that's going to give me 5x. Accidentally here, again, this doesn't always happen, but it happens to be kind of nice that it's happening with this one. The y's actually 0 out, the z's also 0 out, and I'm actually able to, in one step, have a solution for how I could at least get the x value for this solution set. So for this one, it would just be, now let's divide the 5 over, and we can now see that x would then equal 3. But generally, let's say that didn't actually work to where both the y and the z eliminated out. what I would generally do after that is then take a different pairing. So I could go with either number 2 and number 3, or I could go with number 1 and number 3. But I basically just pick any other pair that I haven't done yet, and just try and eliminate the exact same thing. So let's say hypothetically I did that. Let's say maybe with the 2 and the 3. Yeah, then why not? So if I did 2 and 3, how that process would go is I would need to actually scale the number 3 by multiplying by 3. That way that actually they would match. So if I did that, the first one would be 4x plus 2y minus 3z equaling 4. But then the second one, if I scale it up by a factor of 3, I'd now have 9x, a positive 9y, a negative 3z, and now it would equal 12. And if that happened to be the first pair I chose, you can kind of see like, okay, this is now, if I were to, looks like I need to subtract, it's going to give me an equation or a new equation that has still 2 of the variables, not like the number 1 and number 2 where it actually turned into only 1 variable. So if I did that, this would be now negative 5x. I'd have now not positive, but negative 7y. The z's do cancel out, and then 4 take away 12, I could say is negative 8. Now, even though I didn't have to do that for this problem, notice that actually does give us now something where I only have 2 variables to worry about. So I could now go ahead and just I was able to find the solution here for our y. Sorry, not for our y, but for our x. So I should be able to then substitute that in this spot. Turn that into now what? Negative 15, take away 7y equaling negative 8. And now that opens up the avenue of being able to actually solve for y. The other option I could have done is just, since x is supposed to equal 3, I could have gone back to any of the originals and actually just rewrote all of them using an x value of 3, and then I could have picked any 2 of those, and I would have a system that has y and z. But again, it's just a matter of which way you want to go about doing it. The way I'm currently modeling, even though I did, yes, get lucky that I got an x equals 3, I still generally want to take any 2 pairs, try and eliminate the same variable, and then reassess to see what things I can maybe do to solve the rest of the way. So here it would be, let's substitute that in, like I said. Let's go ahead and start moving some things around. So it looks like I can add 15, and I get negative 7y equals positive 7, and then divide by negative 7, and I get my y is equal to negative 1. So as you can see, this is starting to confirm our solution from the previous one, where we have an x value of 3, a y value of negative 1. At this point, to get our z, we basically just go back to any of the originals and substitute in, and then just isolate. So if I go ahead and maybe choose the, I don't know, let's go with just number 1, back substitute what we just got. It would be our x is 3, take away 2 times our y, which was negative 1, plus 3z is equal to 11. And then simplify the best I can. So this looks like 3 plus 2, so that's really a 5, plus 3z equaling 11. So I could then take away 5 from both sides, get 3z is equal to 6, and then divide by 3, and I get my z is equal to 2. And in the end, I just go back and write my ordered triple, in this case, where x goes first, so 3, our y is negative 1, and our z is 2, which does in fact, I guess, verify, since we did do a second strategy. It confirmed our answer from our previous slides. So again, we could go back and double check if I hadn't done the other strategy by just plugging it back into each of the equations to see if it's true. But again, as I can see here, it is the same. But anyway, hopefully this has been helpful as far as giving you strategies on solving systems of equations. But like any other time, if you have questions, by all means come find me and we'll get it figured out. Thanks for taking the time watching the video, and we'll check you later.